The next question of code force is round 918 div 4 is bicycles.
So in this question, we are given with n cities, right? N cities are given and numbers are from 1 to n, right? And along with the cities, they are also given that the cities are connected with undirected edges or undirected roads.
Yeah.
Right? Each edge is represented by UI, VI, and WI.
Yeah.
Where UI, VI are the nodes which are connected, and WI is the weight of that edge.
Weight of the
right?
edge, yeah.
Now the person called Slavic is starting from node 1 or city 1 and wants to go to city N through intermediate nodes like node 3, node 4, node 5, node N. Right? Each edge will have some weight, and if the person wants to go from node 1 or city 1 to city N, he has to use a bike.
Yeah.
Right? They have also said that each city has a bike. Let's call this as B1, B2, B3, B4, B5.
Yeah.
Right? Now, when the person is at city 1, he can buy this bike B1, and using this bike, he can go to the next city.
Yeah.
Right? And whenever he goes to the next city, the time taken to go to the next city is Wi into Si. Now, what is this Si? Si is, sorry, Sj. Sj is the slowness factor among the bikes that he has.
Yeah.
Right? He can choose any bike that he wants to travel from one city to another among the bikes he owns. Initially, he does not own any bike. And when he's at city 1, he can buy this bike B1. After buying, this B1 has, let's say, a slowness factor of S1.
Yeah.
So in order to go from city 1 to city 3, he'll use Wi into Si time to go from first city to third city, where Wi is the weight of the edge from 1 to 3, and Sj is the bike that he chooses, the slowness factor of the bike that he chooses to go from first city to city number 3.
City
right?
number 3, yeah.
So from third city also, he has to go to the next city, which is, let's say, city number 4. So if he wants to go to city 4, he can either choose that same bike that he already used, or he can buy the bike 2, right? So if he buys the bike 2, there is some cost involved, and this cost is irrelevant.
Yeah.
He has infinite amount of money, so he can buy any number of bikes.
He can buy.
So after buying B2, he has a choice of choosing which bike to use to go to the next city.
Yeah.
Right. So let's say there are two bikes S1 and S2. Bike number 1 has slowness factor S1. Second bike has slowness factor S2, and the time required to go to the next city is Wi, which is the weight of the edge involved, into S1, or Wi into S2.
Yeah.
Right? Among these two, whichever is minimum, he'll choose that, because this is the time required to go to the next city. And if we want to minimize the time in which person is going from city 1 to city N, right?
Yeah.
That is the question. So we'll be given with the entire graph, where each edge will have its separate weight. Along with that, we'll also be given the slowness factor of each and every bike, right? Using this data, we should tell what is the minimum time in which the person can go from city 1 to city N, right? And here, the cost involved in buying the bikes is irrelevant. He can buy any bike at any point. Whenever he reaches that city, he can decide to buy that bike.
Yeah.
So looking at the constraints of the question, we have given that there are t test cases. Each test cases are in the range of 1 to 100. We have also been given that n cities are there, where n is in the range of 2 to 1000. And given that m edges are there, right?
Yeah.
M edges are nothing but roads, are in the range of n minus 1 to 1000. And we are also given that ui comma vi will be the edges, right? Will also be in the range of 1 to n. These values will be in the range of 1 to n.
Yeah.
Where ui will never be equal to vi, right? They are distinct elements. And the weight of each edge is in the range of 1 to 10 power 5.
Yeah.
Now, along with that, we are also given slowness factor of every bike. slowness factor of every bike is in the range of 1 to 1000 again. Okay. And it is a condition given that the person should always start from city number one, and should go to city number n. And in this process, we should find out the minimum time in which he can go from city 1 to city n.
Yeah.
And the time required to go from one city to another city is SI into WI, where SI is the slowness factor of the bike that he's using, and WI is the weight of the edge that he's traveling. This is not SI, this is SJ, because among the multiple bikes that he has, he can choose any bike to go from that city to the next city.
Yeah.
That is the question.
So basically, in this question, we have a graph, right? Something like this. Let's say some random graph we have. And the nodes are numbered 1, 2, 3. So these are the cities. From city 1 to city 8, we need to travel. And bikes are also available. Bike 1 is here, 2, 3, 4, 5, 6, 7, and 8. And each bike has some slowness factor which is given. So now, to solve this, if we look over, we have some weights to the edges also. This is W1, let's say. W3. So let's give some random weights. Right?
Yes.
So there are 9 edges here. So there are 9 different weights. So now here, if we observe, our aim is to travel from 1 to 8, right? And we can see that W1 weight is greater than 0, and slowness factor is also greater than 0. That means slowness factor into weight of any ith thing, slowness factor of any j and any ith weight will also be greater than 0. Right? So that means for every edge, whatever weight we are getting, we don't know what is this, but ultimately if we know this, then product of this will always be positive, because this graph has all positive weights. We can see that every path, as we pick a path, the path's distance will monotonically increase. It will either increase or remain same, but it will never decrease. Because that monotonicality holds, we can perform Dijkstra on this. So now our aim is to find out the shortest path to reach from node 1 to node 8, right? With the following routes. So for that, the issue is, if only the dependency is with the WI, we can just do a standard Dijkstra. But here the dependency is on WI S of J also, right? So for that, we can just define something called time I of J. So firstly, before moving on to this, the prerequisite for this problem is Dijkstra. So before watching this editorial, firstly go through Dijkstra and then watch from this point. So this is what is the prerequisite. So now let's define time of I of j as per our Dijkstra. So it is like from node 1, what is the minimum time we took? This stores minimum time taken to travel from node 1 to node I, right? with a bike uh, j, where jth bike is the slowest factored bike among all the bikes that he bought. because we can observe one thing, that is, if slowness factor is more for a bike, then it's useless for him to use. If he bought 2 to 3 bikes, then it's always better for him to use the bike with the smallest slowest factor, right? Because that will actually reduce the distance as we multiply slowness factor with weights. So so now we can define it as minimum time taken to travel from node 1 to j, 1 to I, where, okay, 1 to I, using jth bike. And we know that jth bike is the bike which is smallest among all the bikes that he purchased. Smallest is the smallest slowness factored bike among all the bikes that he purchased. So this is the time that we are defining. Now let us see how we can actually make transitions for this. So let's say we are on node U, and before making the transitions, let's look at the base. Initially, he's at node 1, right? Node 1. And will he have any bike initially?
Initially, no.
No, right? So we can just denote it with 0. 0 tells us that there is no bike. We are assuming that bikes are ranging from 1 to n. And 0 is some invalid value. We can just put an invalid value. So this will be 0 because he requires 0. He traveled for 0 time and he's on node 1. Right? Now let's make the transitions. U is my U is the, let's say U is the node till which we traveled from 1, and from U we have a neighboring called V. So for any neighbor, this transitions will satisfy. So for this, let's make the transitions and let the current bike be J. J is our current bike. Using bike J, we traveled U. So using bike J, we traveled U, and let W be the weight. Okay? So now the way we can make the transition is, firstly, to move to V, which bike do we need to select is the question, right? We can select greedily. That is, if jth bike is 0, that means we should forcefully select the next bike as, I'll mention it as NJ. NJ means the next jth value. So NJ should for sure be U, right? Because U will be the bike's number in city. Now, else, because if it is 0, that bike itself is invalid. This will only occur when we are at node. Now, if we are on other node, if it depends on which bike has the smallest slowness factor. If jth bike has greater slowness factor than the youth bike, then the next J would be U, right? Because for him, money doesn't matter. No matter, he can purchase all the bikes. Similarly, else, that means jth bike has a smaller or equal slowness factor. So next J would be next bike that he'll pick would be J. So here, because he had two choices, he could either pick J and go to city V, or bike U and go to city V. So we just greedily found out which bike he'll be picking. Now we know the next bike which he'll use to go to city J. So now let's see how the transitions will look like. If the time taken to reach city V with the current bike that he decided to pick, if this time he might have reached the same state previously also, right? So compared to the previous state, if we have a better time now, then it's better to explore it. So previously he visited it with, we know the minimum time took for him to visit the state node V and the bike engine, right? And in the base, initially we kept time of 1 of 0 as 0, as he's at node 1 and with 0th bike we are assuming he came. Now for all other cities, we can just initialize it with some higher value apart from this. For all other I and j, it can be equal to infinity. Because we still didn't explore it. Now we are exploring. So because we didn't explore it, we can just fix it to some higher value. So now time of v of nj, if this time is greater than, that is, this is nothing but the minimum time that the person took to reach node v with bike nj, right? So if this time is greater than the current time he's taking to visit to reach it, that is, he'll be reaching uh, from the state node u. So basically, time took for him to reach node u with bike j plus the time that he's taking currently. Right? So the time that he'll take currently is s of nj into the next bike, because this is the best choice for him, nj into the weight of the edge, right? So with this time, he can actually visit V and NG. So that means if this is the case, then because we found a better time, we can just fix it to, into W. And we can just explore this. Now explore V in Dijkstra. So this way we can just make the transition uh, in Dijkstra. So now we can push this into a queue where into the priority queue, where the priority queue, as we know in Dijkstra, priority queue sorts it based on the time phase. So that way we can just insert into the queue and then find out the best time that we have till now and explore that. So so now we can actually look over the pseudocode. So before pseudocode, we found out the base and transitions. Now, what will be our answer? Our answer would be time taken for us to reach n with any bike, right?
Minimum of
With any bike. So that means it's minimum of n with j, where j ranges from 0 to n.
yes.
So we can just find this out. This will be our answer. So this will give us the minimum time taken to travel from 1 to n, where we ended up with jth bike. So now let's look at the pseudocode. So in the pseudocode, this represents minimum time. So initially, let's say the dimensions of it are n plus 1, n plus 1. So this is initially, let's initialize everything to infinity. Now our base condition is 1 of 0 should be equal to 0. Right? At 0 time, we can be at node. So now let us do the queue thing. So for now, let us assume that queue is a priority. Queue is a heap queue. So I'm not following any syntax here. Let's say queue is a heap queue, and initially we can just push 0, 1, 1, 0, 0, 1. So this means this tells us, firstly, let's come from reverse. This will tell us the city number, which city we are. Initially, we are on city 1. This will tell us which bike are we using currently. Initially, we are using bike 0. and this tells us the time that we took to reach this state time. So as this is a priority queue, our aim is to sort it with respect to, we don't care about these values, but we should sort it with respect to this time. Smaller, always we should explore the one which has smaller time, right? As per Dijkstra. So now, okay, let me just put it like this. So this is how it looks. While queue is not empty, I'll just write it as queue not empty. Until queue is not empty, that means we have more to explore. So now, let t be the current time, t be the current time, and bike be the current bike. Okay, let me define it with the same variables. Let j be the current bike and u be the current city. I'll just write it as q dot pop. Maybe this syntax might not be correct, but ultimately you can assume that this q dot pop will give out the value whose time is smaller among all the things which are there. Smaller, it gives out smaller time. Smallest time, basically, smallest time occurrence in the queue. Now let's make the transitions. Firstly, if t is already greater than the current time, that is already greater than time of u of j. Basically, this t tells us that we came to u to j. We came to node u with byte j with a time of t, right? That's what this tells us. If the updated time itself is already smaller than t, then it's useless exploring, right? So that is why we won't explore in this case. So we can just say continue here. Basically, we are not allowing this to go down. So that's why I would continue. Otherwise, just write if it is smaller than or equal, then only enter. It will never be smaller. That is because always we push always we push value, like whenever we push something into the queue, we'll keep updating this, right? So because of that, we can guarantee it will never be smaller. T will never be smaller than the current best time that we found. So now till here we handled, and this t can be larger at a point. So if t is larger, we don't want to explore the edges multiple times, because for every redundant state, for every redundant j comma u comma j pair, we might explore edges redundantly. We might explore edges multiple times. Right? That would actually make our Dijkstra's time complexity time complexity more. So it would execute slower. So just to cut off that iterating over unnecessary edges, we can cut off this value here itself. For all useless states, let's not even explore edges, because we know for sure no neighbor's value gets updated when this is true, right? So that's why we can ignore it. Now let us iterate over the edges. So I'll just let me write v and w. V is nothing but the neighbor of u, and w is the weight between the edge u to v. Let's consider that. Uh, let's say we already built adjacency list. These all are adjacent to u. Right? We are exploring the neighbors of u. So in this case, now comes the transition part. Right? So before transition, we didn't make the bike selection. Right? So firstly, if whatever bike we have j, that is 0, then we should forcefully pick our next bike would be u, right? U itself. Else, there are two choices, and among that, we'll pick the best choice. That is, if slowness factor of bike j, if this is greater than slowness factor of u, then the next bike that we pick. So NJ represents the next bike that we pick. Because if we, just like previously we saw, for every node we have two choices. We can continue with the same bike or buy a new bike in the current city. So here it is better to buy a new bike. Else it is better to continue with the same bike. Right? Now let us write the transitions for this. For v comma w, where v is the neighbor of u and w is the weight between the edge of u to v. ADJ of u will be the adjacency list, assuming we already built it. Now comes the transition, that is time of u, okay, time of v, because we are moving to v, right? If the state, if the minimum time taken to visit the state v of nj is greater than the current time that we are taking, then it's beneficial to explore that, right? And we can guarantee that this will only occur once, uh, as we are performing Dijkstra and path is monotonic. All have positive values. Because of positive values, path's value will always be in Dijkstra. So u to j, time taken to visit to reach till u plus uh, it's the weight of the current edge into slowness factor of the current bike. So this would be the transition. If this is the case, then it's beneficial to update. If this is the case, then we need to update this, right? Because we are visiting the state v nj with a smaller time, which is beneficial. J plus nj. Right? So now we'll be pushing q dot push, assuming that we are this q is a priority queue, and I this syntax might not be present, but the ultimate aim is to push into these priority. Pushing time of v nj comma v, okay, comma nj, as we are maintaining the order as time, bike and city. So nj comma v, right?
Yes.
So now ultimately here we assume that priority queue is sorting based on this value. These values might or might not be sorted, that won't affect us. So the next pop that we do, that will always retrieve the one which is which has smaller distance from one to that one, right? Over here. So this way, once we perform this, yeah, once we perform all these transitions, and once the queue becomes empty, we can guarantee that we reach each and every node which is possible. And in the question, it's guaranteed that for sure he can reach from one to n. There exists at least one path. Because there exists at least one path, we can guarantee that for sure time of n will never be time of basically will for sure visit n at least once. There will be one path. So there won't exist any invalid case here. So that is why finally our answer would be the smallest time. Basically, answer represents the smallest time taken to reach, to start from one and reach n, will be minimum among all the nodes, minimum among all the paths from 1 to n. I mean, it is the minimum time that we took to reach n from 1 with a bike of j. And this j will vary from 0 to, as there are n bikes, and 0 is also invalid value that we checked. So this will be our answer. And if you look over the time complexity, it would be big of n into m, as as we see in the queue, number of states that we push into the queue in the worst case would be n into m, right? where every n and basically I and j that we are putting, I can have values up to n and j can have values up to n. Into again we get a log factor, because in the worst case we know priority queue or heap queue, anything that we use that takes log of n into m to rebring the smallest node to the top of the tree, right? So that is why it gives out a log of n into m factor also. And space complexity would be big of n into m. Right? These all are per test case. And here n and m both depend on the test cases. It's guaranteed that sum of n will be less than or equal to 1000. Sum of m will be less than or equal to 1000. So we can assume there is one test case with n and m perfectly 1000 times. So this way we can solve the problem.